Hello, everyone. Good morning. Welcome to today's workshop. Let's wait a little bit for everyone to connect. Okay, I see a lot of people joining. Okay, so maybe in the meantime, I just introduce myself. My name is Paola Maio. I'm an EU project officer at the European Heat Pump Association, and I will be your host for today's event. Okay, before we dive in and start to introduce you to today's topic, maybe just to see if the audience is here, is ready to start. Maybe you can already share in the chat where are you connecting from. So we will have a little statistics of who's listening. Of course, Brussels, India, Italy. Okay, I think Europe is quite covered. Greece, France, Sweden. Okay, another one from India. Great. Germany. Okay, perfect. And actually, speaking about other countries, I'm happy to share with you that this webinar is in organization and collaboration with two other vetted partners that represent France and the Netherlands. Here with us, it's the International Institute of Refrigeration, represented today by Anna Pacak, and the European Energy and Climate Policy Institute with us, Cristina Casciascia and Giulia Baldelli. Thank you for joining us. Okay, I'm glad to see that so many of you already joined us for this interactive session. So we can start and maybe have a little look at today's agenda. We will start with a brief introduction of the BETTED project and explore how this project actually supports the decarbonization of the dairy sector. And then we'll move through a series of expert presentations covering the use of heat pumps, biogas, and efficient cold change. And then we'll wrap up with a sort of tutorial of the BETTED toolbox and an open Q&A. One last thing before we moving on to the presentation. In Teams webinar, participants are not allowed to turn on the camera and the microphone, but you will still able to write in the chat or in the Q&A section. So if you have any questions or you would like to ask directly to a speaker a question, please add it in the chat. Maybe by tagging the name of the speaker so that we can take care of it and address it later on. Okay, so we can start with a short overview of the BETTED project. BETTED stands for Boosting Energy Transition of the Dairy Value Chain. This project started in February 2024 and will end in January 2027, and it's funded under the LIFE program. And its main goal is to drive sustainable energy practices within the dairy sector by helping companies, especially SMEs, to accelerate the adoption of energy efficiency measures. Here you have an overview of the project consortiums. The coordinator of this project is the University of Brescia, and the consortium is a balanced mix of research, consultancy, energy agencies, and federation of companies. Also, several partners have been involved in energy audits, providing a good basis for this data access. To give you a little bit of background and on why this project have been founded, actually today in this sector, there's a lot going on between the milk extraction and the consumption of the final product. So a lot of work, a lot of processes, and a lot of CO2 emission from farming, milking, milk storage, processing until the final transportation. Indeed, the whole dairy value chain contributes with 4% of the global greenhouse gas emission to the atmosphere, deriving mostly from energy use and varies across the whole value chain. That means that only acting upon each step of that value chain and promoting a cross-level collaboration can the sector be truly sustainable. And that's what exactly we are trying to implement with this project. In this slide, you can see the traditional dairy value chain that we actually want to transform into the bettered dairy value chain. We actually propose to boost energy efficiency by combining renewable solutions like biogas and high temperature heat pumps with other energy saving measures. And why this is relevant today? Well, because biogas alone could replace up to 30% of fossil fuels in the sector by 2030, and high temperature heat pumps can cover wasted heat and reduce energy consumption by about 40%. Together, they create a smart and sustainable cycle. As you can see, farm transform waste, such as manure or bioproducts, into biogas and renewable energy. This energy powers then heat pumps and chiller that cover the heating and cooling needs of the dairy industry. And then the remaining bioproducts are sent back to the farm, closing the loop and restarting this efficiently, smart and sustainable cycle. So in the end, everyone in the chain benefits with lower CO2 emissions, lower energy use, and of course, lower costs. Of course, now you may wonder how we are going to foster this transition in the dairy sector. Where to achieve this, the project focuses on three main pillars. So we will implement a dedicated capacity building program to help both small and large companies improve their skills, knowledge, and awareness about how sustainable value change can drive the energy transition. So we have designed and implemented tailored and easy-to-use tools that engage companies working within the same value chain. These tools will help foster the market uptake of energy efficient and sustainable measures and assess the multiple benefits that can come from collaboration between large and small companies. And finally, of course, we will provide also policy and regulatory inputs to help accelerate the energy transition across the whole sector. Now we can take a closer look at the capacity building program, which is really the core of the BETTED project and also the main reason we're here today. This program is built around 4 key steps. First, we'll have interactive training session with large companies and their value chain partners, aiming at improving their skills and know-how on potential sustainability practices. Second, we will organize around 20 workshops divided between all the project partners with different stakeholders from the dairy sector to exchange best practices and discuss energy, sustainability, and funding opportunities. And then we already have launched actually an e-learning module to make this training more accessible to everyone. And finally, we will carry out direct interviews and roundtables with companies along the value chain to collect insight and foster collaboration. So if any of you join this webinar, this workshop today, is part of the dairy value chain and is interested in joining the better trading activities, feel free to reach out to me. Just a few words on the learning platform. It's one of the key elements of the BETTED project. So to make the training activities accessible to a wider audience, we've developed an online platform open to professionals from both participating and non-participating countries. This course includes 16 training topics, and each topic comes with a presentation, which is the main learning material, and a training handbook summarizing the key points. Participation is open to all professionals and those who complete all modules and fill out the evaluation and final questionnaires. We will receive a better certificate. So if you would like to take part or explore the content, you can access to all the topics and all the courses directly at the Escansa website, which is a partner of the BETTED project. And all the topics are translated in all the partner languages. Okay, so that was in short an overview of the project, and we will dive more into the toolbox at the end of this webinar. So if you're interested in that part, please stay until the end and don't miss the presentation of the tutorial of this toolbox and how it works and how it can help really companies to measure the sustainable practices. So we can, if you have, of course, any questions about the project or would you like to know more, please write it in the chat. I will be happy to answer. And now it's time for our first expert presenter. Please let me introduce you to Damien Casetta. He is EMEA Heat Pump Manager at Armstrong International. In this role, Damien leads the development of Armstrong industrial heat pump range, working closely with R&D teams and production sites, while also providing technical support across the entire EMEA sales organization. He brings a strong technical background and deep knowledge of both the markets and the product lines, which allows him to actively contribute to deployment of Armstrong International Circle Thermal methodology. Let me also specify that Damien contributed to the development of the training of the BETTED project regarding, in particular, heat pumps in the dairy industry, and will be also involved for the next workshop and training organized in the framework of this project. So thank you, Damien, for your contribution, and please, when you're ready, the floor is yours.
Thank you, Paola, for the introduction. Hopefully you can hear me well. And I've taken control so I can move the slide. Good morning, everybody. Thank you for joining the webinar. I'm happy to drive you through this topic, which is heat pumps in the dairy industry. And the agenda for today is to start with an introduction on both the dairy sector and the heat pumps, go through the sink and the source temperatures in this industry, explain what's the pinch methodology, how it can help integrating heat pumps, how we fine-tune the design of heat pumps to optimize efficiency, and then go into a practical case for pasteurization in an ice cream manufacturing plant. So let's start with the basics. Dairy products manufacturing, they all start with raw milk, as you know, and products, they range from various types of milks, powders, cheese, yogurt, butter, and ice creams. The underlying manufacturing process involves thermal processes. Think about pasteurization, sterilization, evaporation, drying, fermentation, cleaning, and cold storage. They all need heating and or cooling. But what's a heat pump? And how it's linked to this heating and cooling needs? Well, a heat pump is a thermal machine that is using a refrigerant as a glue for heat, meaning that it is absorbing heat from a source, say differently, it's cooling the source, and then it's injecting that heat into a sink, then producing a heating effect. And to do so, it requires a compressor that runs on electricity that is needed to increase the pressure of that refrigerant from the cold side to the hot side. And that runs in a closed circuit. That's basically what a heat pump is. To define the efficiency of heat pumps, we have the so-called coefficient of performance, abbreviated COP. That's basically a ratio between what you get and what you pay. What you get is heating capacity, and what you pay is electrical power to the compressor, basically. If you're interested in both the heating and the cooling side, then you add both and you get a so-called combined COP. But then there is a lot of details. In the scope of this electrical power, you have various definitions from shaft COP that includes only the mechanical power to the compressor, then compressor COP that accounts for the motor losses, then heat pump COP accounting for all electronics, and system COP. That's really what reflects the OPEX for the customer, as it accounts for all the pumps and ancillaries that are required to make it work. So that's important to have this in mind when you are analyzing the numbers. But even more importantly is to understand that COP is not a constant value, and that changes drastically with respect to boilers. It's not like 90, 95%, and that's it. No, it varies with temperatures, and it varies with the temperatures that you get on the cooling side and on the heating side. You have some curves at the bottom right of the slide. Then you can have a look at the great variations that you can have between 1.5 and 8. And the less you have difference between the cooling and the heating side, the higher the COP gets. So between 1.5 and 8, and comparing to an e-boiler, which is 1, you can understand why it is more efficient. So heat pumps, they come then with benefit. We've just talked about efficiency. So efficiency with a COP higher than 1 means a lower OPEX compared to the e-boiler, compared to fossil-based heating productions. It means also lower CO2 emissions. Heat pumps, they allow to recover waste heat. And if it's required, you can make use both of the heating and the cooling side. What's also important to say is that heat pump is not a new technology. You can see on the slide 2 pictures from industrial processes back in the 70s, 80s of heat pumps installed in Germany. So it's the past, but even more, it's the future. As you can also see, a forecast of development of heat pumps in the framework of decarbonization goals, energy security, that shows 2 digits growth over the next years. So we've just talked about heating and cooling side, and that comes with temperatures. Temperatures are driving the COP, so it's important now to take a closer look at which temperatures and which processes we have in the dairy sector. Let's start with the cold side, which is the source. So where is waste heat available, or where is cooling required? Well, we've summarized this into 3 buckets, basically. From 1 to 5 degrees, you can find fermentation and cold storages through chillers. From 20 to 30 degrees, then you have pasteurization and sterilization. And there, the waste heat is on the cooling water. And then 70 to 200 degrees, then you get high temperature waste heat on hot condensate and exhaust air from evaporation and dryers. And now, where is heating required? Well, again, we split this into temperature buckets. So at the lower end of temperatures, you have fermentation with hot water. Then from 70 to 90 degrees, you need heat on hot water loops for pasteurization and cleaning, CIP, cleaning in place. 120, 140 degrees, evaporation, sterilization, fed by steam or hot water. And above 130 degrees, then heating needs on the supply air for drying processes. Where to integrate the heat pumps then? Various temperatures, various processes. Thankfully, there are methodologies developed back in the 70s, primarily for the chemical industry, but that can be applied also for light industries, among them dairy. This methodology is called the pinch methodology, and it's basically a mathematical method to calculate the maximum theoretical heat recovery potential in a manufacturing plant, where you have dozens of hot and cold streams at various temperatures. So that's really key to get the maximum efficiency and to get it in a systematic way. I mentioned hot streams. Those are all the flows that needs to be cooled down in the factory. And I mentioned cold streams, which are flows that needs to be heated. And what is pinch actually? Well, that refers to the pinch temperature. And the pinch temperature is the temperature level above which there is a lack of heat in the factory and below which there is an excess of heat in the factory. So that basically this temperature is summarizing the needs for heating and cooling in your factory. We can show it in a different way with the so-called composite curves. So if you combine all of your cooling needs in the factory, so all of the flows that needs to be cooled, then you get the red curve. And if you combine all the cold streams, so it's cold but needs to be heated, you get the blue curve. Doing nothing, it means that you have to provide this large horizontal QC, so cooling, to get the red cooled, and you need to provide that large horizontal QH for heating to get the heating done. Thanks to the pinch methodology, you can identify the maximum heat recovery potential such that flows that needs to be cooled, they release their heat to the appropriate flows that needs to be heated. Having said that, you still find some QH and QC, which are way lower than before, but still you have some. Here, the heat pumps comes into play by recovering that QC and pumping it at a higher level to cover the QH. So the heat pump is re-injected that low-grade heat above the pinch point to further reduce the heat demand. And that's the way to integrate heat pumps using the pinch methodology and get the maximum efficiency. But then there are a lot of assumptions to take, and that's what makes this step so interesting. You can have various depth of analysis, the so-called black box, gray box, and white box. And basically, black box, you stick to the utility level, meaning that processes, they are a black box, they are unknown, untouchable. And the white box, on the other hand, means that the process is entirely known and can be modified without limitation. So all of the streams are as close as possible to the process and the products. The white box is leading to the maximum integration potential. Most of the projects, they fall in between in the gray box, basically, to find a pragmatic compromise under engineering judgment. And that's really it for the pinch. But then what's the next step? The next step is to find the right heat pump. Pinch helps determine the temperatures required for the heat pump and gives insight regarding the flexibility. So these are really the inputs that goes into the heat pump design office. And then the heat pump design office has 3 main levers to optimize the heat pump efficiency. Remember, that's the COP. One is to select the right refrigerant. The other one is to design the right architecture within the refrigeration circuits. And the last one is to use efficient component, primarily the compressor. So on the slide, you have an example of a heat pump from my company. The core component that we mentioned, the compressor, is at the bottom of it. I may have some pointer here, wonderful, so you can see. And the cold side heat exchangers are here, and the hot side heat exchanger are here, basically. And then you have the electrical component at both sides. So with the electrical cabinet, there are various other components to make it efficient and to make it reliable. This is only to give you an overview. So what's the takeaway here? The takeaway is that use pinch for the input to the heat pump design and customize the heat pump to maximize the COP rather than taking off-the-shelf equipment. Optimizing COP means selecting the right refrigerants. Here are a few examples of refrigerants that can address hot water needs above 95 degrees or steam generation. So you have those names on the screen. I won't list them all. However, you can see that for the same temperature conditions, they give you different heating capacity on the left and different coefficient of performance on the right. High heating capacity means more compact heat pumps, so less capex, less footprint. High COP means less electricity, then less OPEX. So selecting the right refrigerant is basically a trade-off between this. Additionally, main aspect to consider are environmental aspects, global warming potential primarily, and safety efforts. That comes with the use of those refrigerants in heat pumps, and to make them applicable in a real manufacturing environment. Then comes the architectures of heat pump. So the architecture is how you are arranging circuits and how you are inserting additional heat exchangers beyond the main ones that we've just seen. In this example, we are showing the serial condensers and evaporator technique, which is basically making use of the large temperature difference that you can have between the inlet and the outlet of the hot and the cool side of the heat pump. And with this, you can get a higher COP up to 30%. And the rationale behind is to lower the temperature difference on at least one compressor. So if you don't use it, in this example, you have a temperature difference, which is 60. If you use it, the optimized compressor will have 50. And remember, that difference is driving the COP. So that's really key, and that can drive high benefits. But it requires understanding process temperature requirements very well. So you have all of those temperatures right. And it requires to have customization when you design the heat pump so you can adapt to the process and not vice versa. Another technique is arranging in the right way heat pumps together. In this example, we are showing you the cascade, which is enabling the use of a large lift, so a large temperature difference between the cool and the hot side of the heat pump. And it's basically using different limits of different refrigerant to achieve that lift. Say differently, if you had a single heat pump with a single refrigerant, thermodynamically, technologically, you couldn't achieve that lift. But by combining different heat pumps, in this example, one is going from 17 to 61, and the other one is going from 61 to 120, then you can achieve that large lift by using different refrigerants, different technology, then optimizing each one to get the best COP in the end. Again, that requires understanding the process temperatures requirements and also the heat pump performance and temperature limits. So both product heat pumps and process knowledge to make this happen. Okay, that's it for the basics, the theory. Let's go through a practical example with ice cream production. So I will start very generic, typical heat sink and heat sources that you can find in an ice cream plant. So in the middle, we have a Sankey diagram, which is a nice tool to analyze all the energy flows in a system. And that's for an ice cream plant with a de-steamed heating network, meaning providing heat through hot water loop, HWL in the slide, and without a heat pump yet. And what we can see is that the main source here is cooling, and that's what we have purple here. And the cooling basically is coming through this pasteurization cooling, air compressor cooling, but also mainly chillers. And in chillers, you get heat from the compressor oil coolers, the condensers, and the desuperheaters, which are shown at the left of the slide. So you basically have two temperature levels. You have low quantity, high temperature heat on the desuperheaters and the oil coolers between 50 to 70 degrees, and low temperature but high quantity of heat on the condensers between 25 and 30 degrees. In this Sankey, it's the high temperature, which is then used directly to feed the medium temperature hot water loop at 60, 70 degrees. But you can see that all of that heat lower than 30 degrees here is wasted. But at the same time, we have heat sinks, so heating needs in this plant. Again, on pasteurizers, on cleaning in place, processed waters, ingredients, rework, cleaning water, digesters, but also building heating. Let's take a closer look at the pasteurization process with its own heating and cooling need. So if we follow the mixture entering the pasteurizer that enters at 65 and then goes into this internal heat recovery to get more heat, homogenizers, and heating at 90 degrees approximately. But after that, it's going at approximately 82 in the heat recovery again to get some cooling and heating, what we've just seen, entering the cooling step to get at further lower temperature, and chilling to reach an outlet temperature of 4 degrees. So we see both heating needs, cooling needs, and internal heating recovery. And the amount of heating and cooling needs depend on the efficiency of that internal heat recovery section, basically. So what can be done to improve efficiency of this typical ice cream production? First thing to do is to make use of direct heat recovery. Remember, Pinch is telling us how to maximize this. Here is an example. Source is the oil coolers from the chillers and pasteurization cooling. These two we've just seen in the previous slides. And the sink is the processed water at 50 to 60 degrees. So basically what we are doing here is that we are heating water, which comes at 10 degrees, first going through oil coolers, heat recovery, and then pasteurization. So we go from 10 to 50, 60 degrees by direct heat recovery only. So the only consumption is pumping. No heat pumps, no fossil fuels, only pumping and heat exchangers. That's the first step. Secondly, the heat pumps come into play. Here we have as a source the ammonia condenser. Remember, low temperature, large quantity of heat that in the Sankey we've just seen that was wasted. The heat pump is supporting in reusing that heat and bringing back to the system. And bringing back to the system where heat is needed, here it's on the hot water loop at 90 degrees that is feeding both pasteurization and additional users such as CIP and tank farm. And here it happened that the heat available was at a fairly low temperature, 20, 15 degrees, and that the heat needed was at a fairly high temperature, approximately 90. To efficiently provide that lift, we use the cascade, this technique that we've seen in previous slides. So by using two different heat pumps with different technologies to lift the heat in steps, so from 15 to approximately 50, and then from 50 to 90. By the way, you can have different projects where that intermediate temperature level at 50 could be used for other needs, such as building heating. So that's a smart way to lift heat efficiently and with possibility to have some flexibility as well. And then that comes with a COP of 2.2, 2.6, depending on the details. And that basically is way more than one. And the total efficiency of this case study must account for both the heat pump, but also the direct heat recovery, which comes with an infinite, if I can say, COP. So that's really the combination of both, which would have been dictated by pinch or similar methods, that is defining the system COP, and in the end, the customer OPEX. Okay, time for a wrap up. So we've seen that heat pumps match dairy needs. They basically provide heating or heating and cooling and are ideal for processes like pasteurization and cleaning in place. Customization is key to performance. Tailored heat pump architectures are essential to meet specific, large temperature lifts and maximize efficiency. The system efficiency, the system COP, is the right metrics. Integrating heat pumps at the right sink and source and maximizing direct heat recovery leads to this highest system COP. For this, the pinch methodology helps. And this is scalable beyond ice cream. We've seen a proven success in ice cream production implementation through a case study, but the potential is important in butter production, milk production, yogurt, anywhere you have pasteurization, CIP, but also there is a great potential in processes such as powder milk using spray dryers. So that's it for me. I'm happy now to take some questions in the chat. Then in some minutes, I have a hard stop. So we will do our best to address even after the webinar if we have no time to address all of the questions. Thank you for listening.
Thank you, Damien. Thank you for your presentation. I think it was really insightful and also clear for non-technical professionals. Since we are still a bit ahead of time, I think that if anyone has a question in the chat, we can also address it now. In the meantime, maybe I can ask you one question. As you said in your presentation, heat pumps are not a new technology. And as they comes with lots of benefits, why today they are not widely deployed? What are the main barriers and how that can be overcome, in your view, of course?
Yes, sure. That's a great question. And one thing is heat pumps are not a new technology, but we've seen recent developments. And when I mean recent, in the last 2 decades, regarding temperatures, for instance, that widen the scope of application of heat pumps in industry. Heat pumps at 80 degrees are possible since 2005, 90 degrees approximately 2015, and heat pumps at 120 degrees, so hot enough for steam production, spray dryers, since 2020. So the scope of application has widened quite recently. So that's one thing. It couldn't be applied everywhere, so it was limiting the potential before. Then the economics of the project is also important to consider. And for this, there is the difference between the gas and the electricity price, so the spark ratio, which is making projects economically viable or not. So here there is a need for better policies, fiscal policies, to get this right, to make it economically viable for stakeholders to implement heat pumps as well. So we see different trends in Europe on this, which makes heat pumps more or less economically viable. But last but not least, what we need is to get everybody trained for optimal integration of heat pumps. If you don't integrate well, then you can get a system COP of 2. And if the difference between gas and electricity is 4, then there is no payback. But if you get it right, use the right methodologies, combine the knowledge from the process, the utility, and the heat pump technology, then you can get system COP above the ratio between gas and electricity, and it's then decreasing the OPEX for the customer. So many thoughts on this. We can. It doesn't cover whole reasons, but that's my view on it. Thank you for the question.
Yeah, so I see that, of course, a combination of all the factors is required to boost this deployment. I see there are two questions, two or three questions in the chat. Maybe we can address some of them.
Yes, sure.
So Saravanan asks us, what is the typical payback period while shifting to heat pump with combined heating and cooling from the individual conventional system for both heating and cooling?
Yeah, that really depends on the electricity prices, the gas prices, and the project. So I would say there is no answer, no universal answer to this, or so it depends on the subsidies if they are. Now we see very good news on that regard at the European level, but it can range anywhere between a few years and I would say 2 digits. So then you make the project happen or not. It's down to the details, definitely.
Okay. Next question is, do you have any idea with design of heat pumps using water as refrigerant between a heat source and a heat sink in ice water chillers?
Ice water chiller, I don't know this type of equipment.
Yeah.
It's chilled water, right? Close to 2-3 degrees. So this is not our focus. I know there are R&D on this for chillers, but when it comes to heat pumps, in my company, but also in other initiatives, there are R&D to use water as refrigerant, which is not drastically new, because if you think about mechanical vapor recompression in steam networks, mechanical vapor recompression in thermal separation processes, like in breweries or in sugar factories, steam is already recompressed inside the process through steam compressors. So it's not fully new. However, to adapt it to heat pump temperatures and even lower to chiller temperature is a challenge, because water below 100 degrees is in the vacuum, very low density. So you need a lot of volume to produce the capacity, meaning either big compressors or compressors that rotate very, very fast. So it's really a technology challenge. However, there are advancements on this.
Thank you, Damin. Maybe just one last question. Martin said, thank you for your very clear presentation. I have one question. Among the refrigerants you are mentioning as relevant for the dairy industry, I do not see any natural refrigerant. Have you considered a heat pump with natural refrigerant? And if so, why do you think they are not relevant?
So in my slide, I was showing only examples. Examples that was given from our experience. And I mean, my company at Armstrong, we are using solutions with the lower safety effort for the customers. So we are not considering for the temperature, we are interested in flammable or toxic refrigerants. However, they can be a good fit if the safety measures are affordable and accepted for the customer, and they are thermodynamically fit for some applications. So ammonia or hydrocarbons can also address some needs. So the slide was the example driven by my own experience, and at Armstrong we are proposing solutions with the least safety effort. That's why.
Okay, thank you so much for your time, Damien. I see that we have also another question on the Q&A, so feel free to answer during the next presentation as we move on. So I take control back of the slide, but before moving to the next presentation, I give the floor to Julia from EIECP, who would like to share with you something that is relevant for today's workshop.
Thank you, Paola, and good morning, everyone. Thank you for your participation in today's webinar. So I just wanted to let you know that after the session, you will receive a link to a short Google form via email. So this will be an evaluation questionnaire with the first part that focuses on your satisfaction with the webinar, and then a second part that aims to better understand the energy efficiency measures that are currently being considered within your organization or company. So your feedback will be very valuable to us, and thank you in advance for taking a few minutes to complete it. Thank you.
Thank you,
Paola,
Julia.
back over to you again.
Thank you, Julia. So it's time for our next presentation that will be introduced by our partner from EIECP, Cristina Cachascia. Please, the floor is yours.
Yeah, thank you. So our next speaker is Ioannis Konstas. He's project manager currently at Q-Plan International. He has degrees in social science and politics and masters in international relations. He has more than 20 years of experience in the in project management, in coordination of research, education, and some collaboration, international collaboration initiatives. And today he will be presenting some insights from a EU-funded project, from Alpha EU-funded project, which is related to better projects, especially in the integration of renewable and specifically integration of biogas within the daily chain, which can contribute also to the sustainability of the value chain. So, Ioannis, the floor is yours.
Well, good morning, and thank you for your kind introduction. My presentation will be quite different with the one we just attended, in the sense that my presentation relates more about people in the dairy sector, people in livestock farming, and in general in the biogas value chain, and actually how to incentivize, support, and mobilize them in order to take up investments in biogas. So, as you understand, and also from my background and my 15 years ago photograph, which I should change because now I have a lot of gray hair, this will not be a technical presentation. However, in the particular sector, it is quite important to bear in mind the technologies and the technical aspects, important as they are, on their own, they will not deliver the goods. So Alpha project was a project that me and a team of very able partners spent the last part of the last 3 years, as this is a project that is completed by the end of October, with the aim to unlock the potential of biogas in the livestock farming sector in the EU. But I should say early on that this is not a project that focused. It is focusing in the EU area, in particular countries. However, we strongly believe that can have an impact beyond the European Union borders. And this is an aspect that is very often forgotten, that the EU is and should try and aspire as much as possible to act as an international paradigm in terms of renewable energy, the energy transition, and the fight towards climate change. because we should bear in mind that even if we do our best and all our targets are achieved, this will not be meaningful, as climate change knows no borders, and a concerted international effort is absolutely required in order to be able to produce what we really need. Now, a few words about my presentation. I've already talked about the aim of the presentation. I will address the problem in context to why, what exactly we're trying to do. We tried to do in this last 3 years, describe the main activities, the partnership, some of the main tool that we have, some of our activities, and then I will conclude with the policy recommendations and the application guide, which will be available for you to get and use at your discretion. Now, okay. I want to present the solutions, and these solutions are mainly a set of actions and activities that took place during these years in order to engage stakeholders, inform farmers, and support the decision making. I must also state that these activities were designed and were implemented having in mind a lot how to be replicated and also how to have impact beyond the end of the project, because more often than it should, projects do a lot of things, interesting things in a period of 3 or 4 years. However, they tend to forget that their results should be exploitable, should be replicable, so they will have a much larger impact than just what they can do in 3 years. So we don't miss on this kind of investment in money, time and efforts, and they will further down the road produce as much as possible results, because we need a lot to be done in the energy sector, a lot to be done towards fighting climate change, and also a lot to be done to support the rural sector, the rural areas that are struggling behind and on occasion feel that they are left out. And indeed, we should have in mind that nobody should be left out if we want to get real results that are sustainable, affordable, and meaningful for our societies. Now, the problem in context already hinted more or less. We know that biogas is a mature and available technology, but in Europe and beyond Europe, as I already said, we have not yet been able to tap the full potential utilizing the massive amounts of animal manure that can be used for biogas and biomethane production. And despite the fact that by 2030 they could have been doubled. So what is the main reasons? Well, I think the things that I would say now can go across the board in a variety of sectors. Lack of technical knowledge and skills. I'm not saying that we don't know what to do, but that these skills and knowledge are not spread around, they are not easily available, especially for livestock farmers. Low social acceptance and awareness. Not always all people know that biogas, bioenergy is a renewable source. And from time to time, due to hasty decisions, a bad design, really bad PR, biogas is not considered to be a renewable source, and we miss out on great opportunities. So great societal resistance is developed, and we got the NIMBY effect, and not in my backyard effect, and financial and regulatory barriers, that they are exacerbated by the fact that within the association of countries that form the European Union, the different approaches really confuse the situation further more and diminish a lot the potential that there is for collaboration, for international within the European Union framework investments and so on and so forth. So how we can support rural actors to adopt and implement biogas systems in livestock farming. And in this, I think even the word rural actors, it's really narrow. We need any kind of stakeholder that would be willing to take up and get into this particular ecosystem can be of assistance. So we brought Alpha. I said that we have been working with a lot of people the most of the last 3 years, being part of the proposal writing and the original idea initiation. And colleague brought about this idea, which I didn't write a lot initially. If you think solar power, wind power, they are, the expression, they are more sexy than getting biogas from animal manure. However, it's something that we should, I quickly came to realize that it was a silly thought to do, because there is a lot of potential, and at the same time, the potential in using animal manure for the production of biogas has a series of added advantages and cross-sectoral benefits that indeed make it very interesting and a very valuable solution, as will help the agricultural sector, can help rural areas, can provide additional resources or revenue, can help other industries by providing valuable byproducts, can help agricultural production, and give jobs. It's, at the end of the day, we definitely need, especially in areas that are excluded by the development that might be concentrated in urban centers, more or less. So what we did in these 3 years, well, we designed a project that would offer business and technical support services to livestock farmers, and indeed all stakeholders of the biogas ecosystem, in order to either create new investments or expand or adapt their existing ones. Because technologies that does not stay stable, and on top of that, there's not just technology, regulatory and policies change, and the initial investments that might have taken place 10, 15 years ago have to adjust to new needs that come up, and the technologies that provide new opportunities. On this side, also we created, did a lot of seminars and webinars, seminars in the national languages, and the various countries that participated in the project, and webinars that had a more international aspect, and also that are available for a long time after the completion of the project, in order to ensure that there will be impact even when we just finish the project. And a set of digital tools, simple tools, are not something that, you know, we didn't invent the wheel. However, we have created together with the stakeholders in a co-creation process, these are tools in order to facilitate investment, knowledge exchange, and collaboration in creating new terms, new possibilities for proceeding with biogas investments. Finally, and this is something we completed the last 4 or 5 months, but essentially we have been working for this policy recommendation and application guide for the whole period of 3 years. That means that throughout all the activities, we gathered elements, insight, interacted with the biogas livestock farming ecosystem, gather opinions, ideas, best practices, worst practices, because sometimes mistakes can be more valuable for investors than best practices, knowing what to avoid, intend to provide concrete policy recommendation and policy briefs, but on a pan-European level, but also the level of the countries that we were active. And now I go to where we were active. We were active in 6 European Union countries: Denmark, Belgium, Spain, Italy, Greece, and Slovakia. This is a very interesting choice in the sense that we have various countries of various different potential and different levels of maturity of the biogas market. And this gave us, the design was such in order to make sure that what we're going to do will be replicable in a variety of setups and therefore be more useful for ensuring the impact of the project. For doing this, we created and established regional hubs. Entities took over the responsibility to act locally in the region and the countries in order to analyze the local conditions and the local value chains to be sure that we will be engaged with local stakeholders in their own languages, be as relevant as possible at the local level, and then facilitate the provision of support. These were operated by various partners, and we were lucky enough to have very strong and really complementary consortium consisting of technical experts, policy experts, associations, consulting firms, research institutes that had we have worked together in the last 3 years. And I have to say, I'm more than happy that the people that joined and worked for Alpha were not just good professionals, but also enthusiastic people about the topic, and they gave their best. At the same time, what was very, very important was the support and participation of the European Biogas Association with their expertise and links and networks within the sector, and the European dairy farmers that made sure that our messages, our work, our material, or our knowledge was able to circulate in large numbers of people that could take up what we did and ensure that the market uptake of biogas will take place. And I think this is a very important lesson that we learned, and I think it goes across the board for all European Union projects, that you should have you should establish good relations, a good net and tap on existing networks in order to ensure that whatever you do, good or bad, will be able to be disseminated widely as possible and therefore have real impact. So I already mentioned the various things that we did, the analysis and the rest, but these were not the main thing. This was a CSA that meant that the analysis of the economic context and the framework conditions really helped us in order to prepare the actual support activities. And the support activities, and now I'm actually more focusing on the ones that took place during the project, and then I will discuss a bit more the post-project surviving activities, were the creation together with the stakeholders of a series of co-creation actions at the local level of business support services for investment in biogas, technical support services and consultancy, the creation of a series of modules for training that was delivered through seminars at the national language of the 6 countries that were active, webinars in English to be able to attract an international audience, and the implementation of awareness-raising campaigns to face the problems that I mentioned earlier regarding awareness and societal acceptance of biogas as a renewable energy source. At the same time, and this is an activity that was one of the most successful, most interesting one, is the mutual learning workshop and field trips. The opportunity to organize trips where people from one country were able to go to another country, discuss, exchange opinions, lessons learned, and at the same visit field sites, biogas plants, and see what the other Europeans were doing and share their experiences. And this has been an excellent process. We didn't have that in mind, that we would get so much information for the policy briefs and the policy recommendations, but they have been excellent activities in more than one ways, and especially for that. Now, beyond the end of the project activities, what we created during these 3 years, I mean, all the things that I mentioned, part of them will be, it is available in one way or another. The webinars, for example, are online, or the description of the services that considered to be fit for biogas, small scale or large scale, are there, available for anyone to get it and use them. And also the raising awareness campaigns, templates, and all these things are there. However, we created tools that we knew would be useful during the project and would be tested, validated, fine-tuned, but be also available after the end of the project, meaning that they will have a big impact that will carry on later on. Among them, the most, let's say, significant is the DSS, the Decision Support Tool, a tool that estimates the profitability and benefits of biogas solutions for each individual case. So you get there, put some basic information, the number of livestock, type of livestock, manure availability, distance to be covered, and all various numbers, and you get an estimation of the potential of profitability. Profitability is something that's really, really important. Yes, biogas is a renewable. Yes, it reduces gas GHG emissions. Yes, it is good for the environment. But if it's not profitable, nobody will take it up. So it's absolutely essential to make sure that someone will invest in something that they will not lose their money, will not lose their time, and also will make the right investment decisions in terms of the various parameters you have to take into perspective before doing it. Because we need success cases. Success cases will bring more interest, more people into the ecosystem, more investments. So it's absolutely important to do what is appropriate for each individual case. On occasion, this can help you realize that on your own, you cannot do something viable, and then you have to assess other options, cooperative option, selling or your manure, or reaching out to form an alliance with other livestock farmers in any other form or context. So this is, I think, a tool that's available online, does not need any help to use it, and is responding to the actual needs, and also is available in the local languages of the 6 countries. An atlas map, a map where you can find in the number of countries where biogas plants exist, for people to realize that there is an ecosystem out there that you can reach out, either to get knowledge, either to visit, either to understand, or just promote your own investment. And this will be updated on its own as we want, because each case can go, anybody can go there and submit their biogas situation there, and after a short audit, this appears on the map. A knowledge center. Knowledge center means that what we did extensive research, and we gathered all relevant material in English or in any other language of Europe that is reposited there and easy to use, and make sure that we tap on all the things that we did, but at the same time concentrate and make easy for people to get the info they need to invest in biogas. And a biogas forum as a place of dialogue. All these are hosted in the Alpha Engagement platform. You can see the link and the QR code. You can visit and you can test them yourself. There's nothing better than doing it yourself and listening to me discussing about it. Capacity building and webinars. So we did 6 seminars at the countries in Denmark, in Greece, in Italy, in Spain, in Belgium and in Slovakia, and webinars which are there available for you to watch in English, of course, and you can get a better idea about Alpha, introductory webinar about biogas and other cases that came up during the co-creation process, a number of topics that are essential for somebody to do that. The other part is raising awareness. Raising awareness was really significant, and what we really learned about the raising awareness on biogas is that different countries or opportunity or different might have different needs. Meaning that, for example, different issues of raising awareness are relevant in Denmark, different in Greece, different in Italy, but there are also similarities. All in all, we did two rounds of raising awareness campaigns, as we did with the provision of support, in which we had the opportunity to apply to do whatever we thought meaningful that we could design with stakeholders, try it, assess the results, and then reapply it in the second round. Our main results are available through the replication guide, and our results showcase that through this approach, 25% betterment of the ideas of the approach about biogas has improved for different set of stakeholders, farmers, general public, policymakers at the various level, to understand the problems, the criticalities, and the actual needs of the market and of the stakeholders, to make sure that farmers, livestock farmers, know that there are possibilities for financial support, because this is an investment that initially is of high cost, and realize the alternative sources of revenues that can be created by biogas investments. Now, I wanted to put a photo, at least one photo, that would be signifying what Alpha was. And also I wanted, this is the first time actually that I'm using so intensively about the mutual learning activities. And this has been a realization that happened in the last 2 or 3 months of the project. Indeed, mutual learning and the opportunity to discuss and bring together members of the ecosystem to exchange ideas, to create trust, to create networks, is one of the biggest benefits that this project created. Indeed, we have created the national networks of biogas ecosystem stakeholders that establish networks, they have contacts, and we have gone even beyond the 6 regional countries. We have people, and only 2 days ago we learned that in Ukraine, participant in one of the mutual learning activities and the capacity building started an investment on biogas, biomethane. This is absolutely insane. No matter how nice it is a technology, no matter how beautiful it can be in the paper, unless you get people speak with other people that have done this, you can never be able to convince them to apply. And the diversity of the cases acted as an enabler for these things to happen, and indeed bring to us into mind that we need to do active real engagement, establish mutual learning mechanism and networking actions that sometimes exist only on paper to be real, in order to be able to transition to sustainable biogas solutions, not as a nice technology, but also an issue that it incorporates a lot of collaboration. I must say that the photo is from Slovakia. This is in the back, the Tatras, a set of mountains that are absolutely beautiful, and we are on the top of that state. We are essentially on top of Manu. I will tap briefly on the policy recommendations. The policy recommendations is the pinnacle of our effort. It means that all our activities, one way or another, led us to the creation of this particular part of the project. The test we started with the test research. I said already about the mapping framework condition, all these things. We got input of all the interactive activities that we did in one way or another. I stressed a lot of mutual learning workshops, but also this was the process that was happening during also the support of cases. We supported like 53 cases in 2 rounds, 53 investments in biogas. And through these discussions, in order to create the action plan, in order to support them, we got so much information that we try to formulate in the actionable policy documentation we did. We also, of course, tapped on external resources. On this, the European Biogas Association reports have been very, very valuable. And even all these things, all this information was coming from the ecosystem and with experts that have real years of experience in the sector. We did again a co-creation exercise, and we discussed again and again. Only last month, the last policy roundtable took place, that we had the opportunity to make sure that what we produce, what we have there is actionable and is real and can make an immediate impact as much as possible. Now, this what you see here is a comparative slide of enablers or barriers in the 6 countries that we focused. This is on permitting, access on finance, grid connection, state regulation and organization, policy coordination, and market safety. So you can see the coloring. The red means bottleneck, yellow means some problems, functionals is green. The champion is Denmark. However, you can see also in Denmark there are issues, and it seems like the common issue for everybody is permitting, and cutting permitting times is essential to boost biogas deployment. All of the lengthy, fragmented processes appears to be the single largest barrier for biogas rollout in Europe. We need to streamline this. We need to make this process predictable. And in this way, we'll be able to reduce uncertainty, accelerate project materialization, and ensure that we don't get a lot of delays that cost money and sometimes disappoint investors. I won't go into a lot of detail. I'll just give you a few insights. In terms of the policy, it's absolutely necessary that the various sectors, and especially at the EU level, need to work together. Biogas is not just an energy issue, it's not just a renewable energy issue, it's also an environmental issue, it's also an agricultural issue, it's also an environmental issue. So we need the various sectors to work together in order to get good results. Sustainability have to take into consideration. This is not, yes, profits, financial profits are important. However, we don't want to replace the fossil fuels with another dirty approach. And this can be a very, very effective and environmentally friendly approach. And indeed can be an approach of circular economy. And this is the future. And also, sustainability has the aspect of social acceptance. We need to make sure that we take into consideration the areas that the investment will take place will be taken into consideration in spatial planning, and also in bringing the local residents on board, not just as an afterthought, but as something that will be taken early on as a prerequisite of the actual investment. You must make sure that the scale and the design of the biogas plant will be well thought. So the economic model you're going to have will not be very fragile. It might be something that is small scale and will cater for particular large level needs, or it can be something larger. You have to take into account the availability of manure. This is not necessarily happening, so in order to be profitable, you must make sure that you're going to have this feedstock on time and work have it. Mind you, biogas can be a baseload energy source. So when you do an investment, you have to make sure that this is not dependable on the sun or the wind. However, it is dependable on the availability of manure and the quantities that are necessary in order to be profitable. And we turned the finger to Denmark for a good reason. That is a very well developed market. Why? For the stability of the framework in terms of financial incentives, and this led to having indeed a well-working market that is state of the art, and a lot of other countries can learn a lot for Denmark. Denmark is very interesting because also it's a huge country, and that means that even for smaller countries, there is a way. This is not a sector that cannot be done equally efficiently in Slovakia or in Greece, countries that have different aspects, if you take into account the points that I just mentioned. The main policy recommendations that go across the board, you can see this one where are more appropriate or less appropriate. Most recommendations are indeed appropriate for other countries that we take into account at different levels, of course. However, it's absolutely certain that this is something that we need to have action now in order to accelerate the energy transition and the dependency of the European energy system to externalities that are beyond our control and on occasion can create huge problems. I must add here that we need to make sure that, and I highlight the need for financing opportunities for both small and large scale, but especially for small scale farms. This will not be only efficient in terms of the energy transition, but also will be something that will help rural areas a lot and small scale farmers that at the same time are much more environmentally friendly to large scale installations. So they're not left out, especially cooperative projects, small farmers need this kind of support and stability that will make sure that they will invest and will be able to get their money back, and this can act as a multiplier in the future. And I mentioned permitting processes that are long and delays and complicated. That means that small-scale farmers are not able to do that, and this is connected also with the scarcity of expertise and consulting. It was funny to see that even in countries that there was a lot of development, there was real need for people that were newbies in the sector, that they needed even the most basics, and there weren't consultancy services available around. I also mentioned the necessity on occasion for cooperation, partnerships among feedstock providers and plants to make sure that the production is available, and also the two interesting aspects that have to do with the secondary, let's say, products of biogas systems, which is the biogenic CO2 that can be sold, and fertilizer produce that is of higher quality and can help also the agricultural production. You can check both in the EU level and the national recommendations for the 6 countries, Denmark, Belgium, Spain, Italy, Greece, and Slovakia, and the pan-European ones, if you scan this particular download and see. And we worked really hard. We interacted with all the stakeholders again and again and again to make sure that they are both actionable and meaningful activities. And also you can check the replication guide. The replication guide is a source where you can also download and check of the various things that we actually used and applied, from the basic stuff, how we set up the hubs, what was the approach for the provision of service to the key account management approach, how we developed the DSS, the decision support tool, and you can use it, the Biogas forum, the Atlas map, the support services, what were the main topics and how we applied them, the co-creation process with stakeholders, that was absolutely essential, the capacity building activities, the ML workshops and field visits, and finally the main ideas about how you can move forward for a biogas investment, going from the motto adopt, adapt, replicate, and this is the idea. And it can be used for a number of stakeholders, for simple farmers, policymakers, industry experts. This is a real guide that you can use to tap on the work we have done in the last year. And we are absolutely excited to complete a sad debate, because we did form a very good collaboration among us. But we are excited on the prospect that the work we did in the last 3 years will have real impact and will help livestock farmers and biogas investors to move forward to a very hopeful and often underestimated renewable energy technology. So thank you for your time. People say I tend to talk a lot, but this is from the experience, from the heart. We spent a lot of time in the last 3 years, something that initially I didn't think was very exciting, but in terms meeting the people, going to the various places, exchanging views, indeed, this is a sector that has a lot of potential and should not be overlooked. So thank you for your attention. And if there are any questions.
Thank you so much, Yannis, for your presentation, and also well done on your project. I think it was really inspiring for everything you achieved during this year. So yes, if there are any questions, feel free to write it in the chat or in the Q&A session. We will address them later, or Yannis can also write an answer directly in the chat. So I think we can move on to our next expert that will be introduced by IIR from Anna Pacak. Please, Anna, whenever you're ready.
Thank you. I'm taking control. Thank you, Paula, for giving me the possibility to introduce Dr. Andres Stamp, the expert cooperating with SEMAPOA and IIR, just before his presentation. So Dr. Andres Stamp obtained his degree in mechanical engineering at INSA de Lyon in France, and after a year spent in industry, he preferred to invest himself in higher education and research in thermal engineering. It was done in the Department of Lorient in University of Southern Brittany. His work in building thermal engineering allowed him to obtain the degree of Doctor of Engineering in Fluid Mechanics and Heat Transfer in 1986 at ENSM in Nantes. He then moved towards the industry in the field of commercial refrigeration and refrigerated transport. His investment in engineering teams Bonnet Refrigeration and Carrier Transicoat has allowed him to develop numerous products and write many articles on evolution of technology in the field of refrigeration. So currently he is recognized as the technical and legal expert in refrigeration at the national and international level, and he has notably represented Carrier within the professional associations like IIR, AFF, Uniclima, and Frigorut, and in France, with the bodies of AFNOR, CIN, and ISO standards. In recent times, he's working as a trainer or expert with Semafroid and now with IIR for audit or some training missions. Thank you very much. And I'm giving you your turn, Andre.
Okay, thank you, everybody. Good morning, everybody, first of all, and the analysis that I will present is more focused on the energy issue and challenges in the farm. So this will be a little bit different as a previous presentation. The content of the presentation is the first slide that you see here. So you will see that I will go through several steps regarding mainly the energy saving that we can do in the production in the farm, in a dairy farm. So as you know, the use of refrigeration is very important. And the cooling of raw milk will increase the lifetime of the milk, first of all. And the different cooling process that you have seen in the first presentation are an example of the application of the different process. And the major disadvantage, of course, is the energy consumption. And it's estimated to represent today 30% of the agri-food industry. And if we add meat, we will arrive at 60%. So this demonstrates that the improvement of energy efficiency is very important to make the dairy industry economically viable and sustainable. If we focus now on a farm, as soon as it is milked, the milk must be cooled as quickly as possible to 4 degrees C to prevent bacterial proliferation and guarantee product safety and quality. The electricity for milk cooling is typically the largest usage on dairy farm. On the picture, we can identify the split of energy. This was a chart done in US, but you can see the milking system and the milking refrigeration and the water heating process are consuming more of 50% of the energy. So the principle of milk cooling is quite simple. The energy used and its efficiency can strongly vary between farms, depending on the size, the age, the location, the number of animals, but also of milk coolers technology, the model, the trademark, installation, and maintenance issue. Slowly, I try to... I have some... Okay. Okay. I'm sorry for the the movement of the slide. Okay, so if you focus on the energy cost, in a typical dairy plant in the EU, the coal production often accounts between 25% and 50% of total energy consumption cost. It is therefore essential to reduce energy consumption. Milk cooling and system for washing make up the largest part of the electricity used by dairy farms. With latest technology improvements, there are generally gains to be made in energy efficiency. The main consideration for improvement energy efficiency includes new technology, upgrading older, less efficient equipment, and improving maintenance practices. The refrigeration unit for the bulk storage tank. Okay, for a milking system, we can have the refrigeration units for the bulk storage tanks, the vacuum pumps, the milk transfer pump, the water heaters, the pre-coolers may be included in the system. Okay, so what is a pre-cooler? A pre-cooler is a heat exchanger that cools milk prior to entering in the bulk tank. And the cooling fluid is usually water. The main type of milk pre-coolers are plate heat exchanger or shells or tube heat exchanger. So you have two pictures that you can see what we are speaking. And heat exchangers are designed to maximize the area of the heat transfer surface, which increase friction and pumping heat. If a system includes a pre-cooler, it's worthwhile adding a variable speed drive on the milk pump. And the energy consumption of the milk tank without pre-cooler is typically 22 watt-hour-liter of milk on average, and it's directly proportional to the temperature of the milk. Temperature of the milk is around 35 degrees C. Consequently, a 1 degree C reduction in milk temperature results in a 0.5 watt-hour-liter reduction in energy consumption by the milk tank. The energy saved by pre-cooling is therefore directly linked to the reduction in the temperature of the milk as it passes through the heat exchanger. Refrigeration unit for milk tank. The refrigeration system No, I have. I'm sorry. I have first to speak about the milk transfer pump. In the installation of a pre-cooling system, it is very beneficial and an optimization for energy consumption of transfer pump is also recommended. Pumps account for 15 to 20% of the milking unit's electricity consumption, with an average consumption of 10 watt-hour per liter of milk. Variable speed drive can be used on the milk transfer pump. It is usually done if the milking system includes a pre-cooler. Instead of directly powering a conventional AC motor that only operates at full capacity, the inverter provides a variable speed drive compressor with a specific voltage required to meet demand such energy saving. It gives the ability to slow the flow rate of the milk through the plate coolers, which greatly increase the cooling of the milk. It has been estimated that the additional cooling provided by using a variable speed drive on the milk pump is an additional reduction of temperature between 8 to 11 degrees C. And the variable speed drive saves up to 40% on vacuum pump consumption. It's also worth knowing that the system is suitable for robotic milking machines. The vacuum pump operates almost continuously, making this installation consume almost twice as much as conventional milking machines. Okay, now we will speak about the refrigeration unit for milk tank. The refrigeration system operates using a vapor compression cycle of refrigerant gas. The mechanical compressor is a component in the refrigeration system that compresses the refrigerant vapor from the evaporator pressure to the condenser pressure, consuming about 70 to 80% of the input electricity to the system. Replacing end-of-life compressor with a scroll compressor, for example, can save from 15 to 20% in cooling cost because of the lower electrical demand. But this replacement is feasible if the new compressor is within 5% of the capacity of the existing compressor and the condenser unit has been well maintained. Currently, existing milk cooling tanks on the market operates exclusively with HFC fluids, mainly R404A. The regulation provides for a gradual ban on certain refrigerant used in the refrigerant circuit of new milk cooling tanks. The European F-gas regulation since the 1st January 2020 as R404A is banned in new equipment because of the F-gas. The new models of milk cooling tanks are charged with HFC with a global potential below 2,500. Notably, R404A will not longer be marketed in EU. So the range of product on offer is therefore bound to change over the coming years. Together with a refrigerant and compressor supplier, manufacturers are looking at an alternative solution that could be brought to the market while maintaining the tank current level of performance. So the system that you will see at the moment is R2L or natural refrigerants. So refrigeration heat recovery unit can be used as a heat exchanger to transfer the waste heat from the hot refrigerant line between the compressor and the condenser to the hot water storage tank. So yes, we have a lot of water heat demand in the farm. And this water can be used as a preheat water source feeding into the water heater. A refrigerant heat recovery unit can cover from 20 to 50% of the energy that would be needed to cool the milk for storage. If a decision is made to include such a device, the usual recommendation is that the heat recovery refrigerant be sized to provide enough hot water for one milking, including washing the system and the bulk tank. The water heater can also be provided by solar panel to save cost energy. An additional electric heaters may be used in the amount of hot water produced by the heat recovery device is insufficient and too low at temperature. In terms of components, it's important to realize pre-cooler and recovery heat device are use waste heat from the milk to use other purposes such as water heating. Consequently, the pre-cooler and the refrigeration heat recovery unit are in competition somewhere in terms of energy saving. And some publications recommend that dairy with less than 100 dairy cows could use either a pre-cooler or refrigeration heat recovery, but not both. Okay. Regardless of the appliance energy, of the appliance efficiency tank, water heaters have different levels of insulation. Okay, here we will speak, I'm sorry, about the water heaters without tank. A standard insulated tank experiences a heat loss of around 60% per day, and the best insulated tank experienced standby heat loss of around 20% per day. A recent entry into the water heating market is a instantaneous water heater, also called a tankless water heater. Tankless water heaters heat the required amount of water on demand and do not have any storage tank. So standby losses are eliminated. They are available in natural gas and electric, but the electric version will not be suitable for this application because of the high power demand they will create. A case study comparing a natural gas conventional hot water tank and a tankless hot water heater for 98 dairy shows a cost saving of 60%, which achieved with the tankless hot water heaters. So just a remark, the installation of solar panels to power refrigeration system is an interesting solution to reduce energy footprint, and the use of renewable energy sources such as solar, geothermal energy reduce dependence on fossil fuels. Okay, just a few words about maintenance of cooling equipment. So we have three parts. The refrigeration system maintenance, first of all. One of the most important aspects of refrigeration management is regular maintenance of the refrigeration system. This includes cleaning and replacing air filter, checking refrigerant leaks, and inspecting components for wear. Regular maintenance ensures that the system is running at its optimal performance level and reduce the risk of breakdowns and repair. So periodic control of refrigerant leaks. In Europe, the F-gas regulation implies a systematic verification of the refrigeration system sealing. This control is very important to limit direct emission of HFC and prevent refrigeration interruption. In case of leaks, the quantity of refrigerant in the refrigeration circuit is not nominal, and the energy efficiency decrease. For the same production of cold, energy consumption increase. And at last, cleaning the surface of heat exchanger. It's very important. Cleaning is important for maintaining the energy efficiency of refrigeration system, especially the heat transfer components of the system. So we speak about the evaporators and the condensers. The appropriate cleaning process can eliminate unpleasant smells that can be emitted from the buildup of bacteria in the system. It also prevents the buildup of impurities on components and reduces fouling on heat transfer surface, ensuring clean heat exchanger surface for efficient performance. It is recommended that adequate cleaning is carried out every 3 or 6 months as part of regular service and maintenance program. Frequent cleaning of a system increases reliability and efficiency, less failure, and provides long-term protection and peace of mind for users. Energy saving practices. Reduction of energy by organization management. To reduce the energy consumption of a conventional vacuum pump, you can also reduce its utilization by adopting good operational practices. These include installation and procedure for utilization. Ensure that equipment is shut off or turned down when not needed by use of timers or controls. Do not start the vacuum pump before picking up the animals. Do not overload cold rooms to allow better air circulation. Make it easier to move the animals around the milking parlor and organize the route to avoid the pump to work for nothing. Do not install the milk coolers in a hot zone or sunlight. Maintain the milk coolers closed all the time. Regularly monitor energy performance indicator to identify any deviation. So we can also optimize the milking time. Keep the cow clean to optimize the time spent under hygiene. Training employees on the importance on energy management. Avoid leaving cold rooms doors open for too long time or to limit cold losses. On the other side, you can increase the automation system and automatic control. Modern technology now makes it possible to precisely regulate refrigeration system. You can manage. It is possible to control the temperature of equipment in real time, to adapt cooling cycle according to needs. Install energy management systems that optimize the use of cold according to peak hours and of peak consumption times. Use predictive control algorithm to automatically adjust parameters based on external condition and heat load. So the installation of remote monitoring systems make it possible to monitor the performance of refrigeration system in real time. These tools make it possible to anticipate breakdowns, quickly identify malfunctions, and maximize energy efficiency. So the next point that I would also highlight is the transportation of milk by road. So the agreement on the transport of perishable food, called ATP, agreement from United Nations Economic Commission for Europe, relates to international transport and the machinery to be used for such transport. ATP is a United Nations agreement signed by 52 countries and set out the requirements for temperature controlled transport. So the agreement includes isothermal equipment, in particular insulated tanks, used for the transport of milk. The purpose of the ATP regulation is to set a minimum insulation level for tanks. Specifically, the ATP regulation imposes certain rules in the construction of isothermal equipment for refrigerated transport. They impose certain prescriptions for the user and prescribe the types of perishable food to be transported under a controlled regime and the temperature at which refrigerated transport must be carried out. Therefore, you have two insulation thresholds that determine the tank used for the transport of bulk milk. First of all, the normally insulated equipment called IN, overall heat transfer coefficient, where the overall heat transfer coefficient equal or less to 0.7 watt per square meter degree C, and heavily insulated equipment where the heat transfer coefficient equal to 0.4 watt per square meter degree C. So while most of the fleet is aligned with the least demand threshold, choosing IR class tanks can generate energy saving. So depending on the length of the journey between the milking center and the dairies, the energy savings vary. In practice, it is also limited by the principle of HACCP, which requires that a temperature of 6 degrees C not be exceeded when the milk is removed. However, in all cases, the use of IR class equipment makes it possible to limit the rise in temperature of the milk and therefore the production of coal necessary for the dairy to maintain the cold chain. So here you have some I'm sorry. You have some references that were used for this analysis. And thank you for your time, for your attention. I am happy to answer questions.
Thank you, Ander. Thank you for your presentation and for giving us an overview about all the refrigerant in this sector. We will address all the questions later on. So if you have any, like before, you can write it in the chat or in the Q&A session.
Thank you.
And now we can move on to our final presentation. So last but not least, let me Beatrice Marchi. She's a researcher from the University of Brescia. They are also the coordinator of the BETTED project. And she will introduce us, give us a tutorial of how the BETTED toolbox works and how it can be a useful tool for companies in the dairy sector to foster the energy transition. Thank you, Beatrice.
Thank you, Paola, for the introduction. And first of all, thank you all for participating, for joining this workshop, this webinar. And as it is the title of this presentation, the aim of this last speech is to provide an overview on the toolbox, on the set of tools that we have developed under the BETTED project. So as previously introduced, one of the main objectives and one of the main output that we developed under the project is this set of tools that which aim to support decision maker inside the value chain. So the approach is not only at the individual point of view, but the focus of the project and also of this set of tools is to support collaboration among the different stakeholders of the supply chain. So starting from the farmer to the ending to the retailer, we consider all these actors that collaborate and aims to provide the final product to the customer. So each of the tools are available on the website, so it can be downloaded, are Excel file tool. So the main idea was to develop some easy to use tool. So the idea is not to provide too advanced tools that are not so fine to support non-expert. So our idea was to increase awareness, increase skills of these decision makers that not always in the dairy sector are focused on the energy aspect. So these 7 tools are offline spreadsheet, so can be downloaded and used on each computer, are in English, and of course are free. So the first tool is the dairy supply chain tool. So as I previously said, the focus is to assess, to map the energy consumption along the supply chain. So it is not an energy audit of a single company, but the idea is to ask few input data to each one of the stakeholders, each one of the actors that collaborate along the supply chain in order to assess which are the most energy consumer and on which we should focus when thinking about energy efficiency measure. So providing very few input, starting for the transportation stages, but also on the production stages and storage stages, few information about the annual energy consumption for the different energy vector, some few information also on the operation of the parameters. So we need also some information about distances, fuel type for the transportation stages, while for the storage and production stages, we need some information about the size of the warehouse, the temperature, internal and external, so some very few input data in order to support the user of the tool in selecting the most promising energy efficiency measure. So as an output, the user can see how the different energy consumption are, the specific energy consumption behave along the supply chain. So for example, in the graph below, we can see which are the stages that present the highest specific energy consumption. This means that we have a kilowatt hour per unit of product, and so we can start to think about energy efficiency measure for these actor, for these stages of the supply chain, instead of the ones that present very low specific energy consumption, so present very low shares of the overall specific energy consumption. The second tool is also focused on the supply chain, so is a simplified life cycle assessment tool. Also in that case, the focus is on the life cycle, so starting always from the farmer to the final retailer. In that case, we move from the energy consumption assessment, so the energy mapping assessment, to other environmental aspects. So also in that case, we ask few input data for each one of the actors involved in the supply chain. And based on this input data, we can assess which are the stages that we should prioritize in terms of global warming potential, cumulative energy demand, and water use. So we selected these three indicators from the LCA, from the life cycle assessment approach, since these are the most relevant for this specific supply chain. And based on the input data, we can increase the awareness of the decision maker, not only related to the kilowatt hour per unit of product, but also considering a broader environmental impact. So based on the result of these two first tools, we can have an image, we can have a map on the stages that are most energy consuming, or on the stages that are that present the highest environmental impact. And based on this, we can start thinking about which energy efficiency measures or which sustainability measure, more in general, we need to prioritize. And going on with the third tool, we can evaluate these measures that we think are the most promising in terms of economic feasibility. So the third tool is a simplified life cycle costing tool, which aims to support the decision maker in order to assess if the measures that have been selected from the first two tools are also feasible in an economic terms. So in that case, also we have an holistic approach, since we are talking about life cycles. So we are considering all the costs that emerge from the investment to the last year of the technology or the measure that we are considering. And the template, the tool that has been developed, support the decision maker in defining which are all the relevant costs that will incur alongside the life cycle. As an output for each one of the measures that the user wants to investigate, there is an economic performance assessment in terms of net present value, internal rate of return, and profit index. In particular, we can compare the behavior of the scenario without any sustainability or energy efficiency measure with three other scenarios with one or some of the measures implemented. These three tools are mainly focused on this procedure to map all the supply chain, select any energy efficiency measure or sustainability measure, and evaluate their economic performance. The next tool is focused on a specific relevant point that is at the center of the project, that is the biogas. So the tool 4 has been developed in order to understand if the biogas can be a solution, a feasible solution for the specific supply chain that we are considering. So also in that case, the tool is similar to the other in terms of template. So we have some input sheet that requires some information about the site that we are considering, the supply chain that we are considering, also including, also in that case, the possibility to having different actors collaborating and cooperating on that topic. And as an output, there are the result in terms of self-consumption, electricity sale, heat sales, and so as the final result, the user can understand, can have a first assessment of the feasibility of implementing the biogas plant. So also in that case, we have net present value, internal rate of return, and profit index. Another tool focused on one specific technologies relevant to this project is the tool number 5, which aims to assess the performance of heat pumps inside the dairy supply chain. Also, this tool is specific to technologies and providing very few input data. The objective was to show if this heat pump, this technology is feasible from the economic point of view compared to a traditional scenario with natural gas consumption. In particular, we provided this benefit compared to the traditional scenario, to the as-is scenario, and provide this sensitivity analysis increasing the coefficient of performance of the heat pumps. So of course, the highest the coefficient of performance, the highest the benefit. And also we investigated the impact of increasing the share of renewables that cover the consumption of the heat pumps. So as also previously has been said, the heat pumps are a great technology for the energy transition, so for the decarbonization of the sector. And so if we think about heat pumps, we also should think about heat pumps integrated with the renewables, for example, with the photovoltaic system, and increasing this share of renewables that cover the electricity consumption, the energy consumption of heat pumps, we also can imagine a zero emission for this to cover this request of energy. The last two tools are not more focused on single technologies, but are mainly focused on cooperation and collaboration among the supply chain stages, so the supply chain actors. The first, so tool number 6 is a dairy vendor sustainability assessment. So is a sort of interview, a sort of questionnaire that allow the stakeholder to investigate how sustainable are its own partners, so its vendors, but also its collaborator inside the supply chain. So there are questions about 4 main areas. on climate impact, biodiversity and conservation, sustainability transition, and social responsibility and governance. And filling this questionnaire is possible to evaluate, to assess the sustainability performance of each one of the partners inside the value chain. So in that case, in order to investigate and to support the result of the first and the second tool, in order to understand which are the worst performing, and also investigate which are the ones that has more opportunity to improve their performance. So the idea is to invest more in the actors inside the value chain that has the worst performance, but also that are far from the best available technology, so far from the best practices. Because in that case, invested as a higher result. So for the profit index, of course, will be higher. As a result, we have the evaluation of each single category, so each single topics, but we have also a radar graph that allow to compare also different user, different actors inside the supply chain. The last tool is the non-energy benefit evaluator. So also in that case, we are focusing not only at the single company, but we are focusing on a supply chain perspective. So the idea is to support the decision maker in identifying which are all the other relevant benefits that are not only energy savings that can occur to different actors of the supply chain. So for each one of the measures that we want to investigate, we can use this tool in order to, the tool provides some example, provides some different non-energy benefit for different categories. And the user can say if this benefit can be applied, this non-energy benefit can be applied to the specific measure that we are considering or not. And we can also define if this non-energy benefit will impact on reducing cost, reducing risk, or improving, creating value for the value chain. And of course, all these non-energy benefits should be evaluated not only based on the single company, but also a discussion on how this non-energy benefit can occur also at different stages of the value chain. So the idea of this tool is to support decision maker in identifying different non-energy benefits, but also support them in the quantification, so in quantifying these non-energy benefit in order to make more strategic the measure that we are considering. Okay. In this presentation, due also to few time, I have only presented the main scope of the different tools, but on the YouTube channel of the project, we have provided more detailed videos. So if you are interested in one or more of these tools and want to have more information, on the Vetted Project channel on YouTube, you can find video that explain also which are all the input that are required and provide some example of the result that you can obtain in using this tool. And of course, if you are interested, you can also contact us in order to provide you more details on the tool and support you also in the use of the tool. So thank you all for the time and the attention, and I leave the floor to Paola.
Thank you, Beatrice, for your presentation. It was really clear, and I really suggest everyone to go and check on the YouTube channel to see the actual tutorial of the tools. And as Beatrice said, if any of you in different companies in the value chain would like to assess and to use these tools and would like to have some support, we can provide it. So you can contact us. You will find all our emails in the Betted website. So feel free to reach out. And we can move on now to the last part of today's session. We can use this part to ask some questions or to discuss with all the speakers that are still here today. I think that Damian had left, but he also answered to the question in the Q&A session. So yes, I invite the audience to write everything in the chat to discuss better any points that have reached the interest of the presentation. And I also invite all the speakers, if they have any questions about other presentation, this is your turn now. Does any of the other colleagues organizing the webinar has other question, also another presentation? Yes, Anna, go ahead.
So maybe I will start. I have a question to Dr. Andres Stamp, because I'm also curious about a few things, but maybe the question is simple, but I would like to ask you if you know like the biggest challenge when applying pre-coolers or some other energy-saving technologies in existing installations in dairy sector. So is it maybe like some challenge with design, or challenge because there is a limited space, or the staff is not trained well for future system maintenance, or maybe it can be some challenge with adaptation of some new equipment to existing system, or not only system but also the other system which are arranging this system that is performing well. So that's my question. Thank you.
Okay, so it's not a simple question, but I think we have two type of work. One work is more, we have to audit probably farms in order to help, so we have to train auditors, which can go to the farms and can help the farmer to make, I will say, energy saving plan and what is the best what they have to do, because it's depending of the size of the farm. On the other side, you have the industry. And the first presentation of Damien was very clear. You have a lot of complete diversity of system. So, and different type of approach of big, I will say, supplier like his Armstrong or Carrier or Daking, of very big players in this industry, and where I will say we have several approaches. It's more complicated on I will say. So I don't know if I can answer more precisely, but for me, you have really two approaches. The help of the academic approach, which was done with different tools which were developed, also is very helpful. We have to train the auditors to use these tools in order to help the auditors to bring back, I would say, the real data and the real argument to find the way for decision.
Okay, Thank you. Thank you. So I have only short question after this. So maybe because it's very interesting, the pre-cooler equipment that we pre-cool the milk and then there are some savings. So is some method currently the most commonly used in the dairy sector? Like it's normal that when somebody designs the system, it's automatically planned that, like heat recovery in air conditioning, for example, you have to design heat recovery because there are some requirements. So the question is like pre-cooling of the milk popular, or it needs more attention for designers? And that's all. Thank you.
No, it's very popular. It's
okay.
It's very popular.
That's
okay.
Yes, that's a good information. Thank you.
In France, I know better the French market. I'm sorry. I have not a view, international view for all the dairy farms in the world.
Yes, of course. Thank you.
I maybe jump in just to also ask a question to Dr. Andre Stamp, because it was a hot topic here in the chat. So what is the position and what do you think about natural refrigerant as of today? And if you already tested the implementation of this type of refrigerants?
Okay, I will say a lot of equipment today are using natural refrigerant, and it's very feasible, particularly in the farm industry, and also for some process that you have in the industry. So CO2 is quite used in several type of equipment. We have a lot of CO2 equipment, and also propane is also to be used, but with a safety problem sometimes, which has to be managed. But ammonia is used in several countries, not really in France, but in other countries. Ammonia is really used also. When I think I have visited ammonia installation in US, you have a lot of installation in ammonia in the dairy industry, and also if you speak about Nestlé, for example, in France, you have a lot of ammonia installation. It's a big player in the dairy industry. So you say the natural refrigerant is somewhere much easier to use when you speak about refrigeration, but it's more complicated when you speak about heat pump.
I imagine.
Okay. And this is one of the reasons that Damien has not a lot of, I say, system in this type of technology. Yeah. Okay.
Thank you so much. I think there is a question in the chat for Beatrice. Thank you for your presentation. Are the 7 tools presented available? If so, where? Yes. Thank you, Anna, for writing in the chat. The tools are available in the Betted website, so you are free to use them. And if you need any support to use them, we are always available to help you. Okay, I see another question from Julia. Yes, please go ahead.
Yes, thank you, Paola. So a question for Ioannis. If he has an opinion on how we could address the permitting barriers that were identified in almost all the pilot, all the targeted countries in the project.
Well, that's an interesting question. Well, the digitalization is the one thing. Scrap the paperwork, create easy-to-use platforms that are interconnected with various databases within the context that you are. So you apply, you present certain number, your VAT number, whatever, then the different kind of checks can be done automatically, and you get answers. So this is a very on-the-spot reaction, but visualization for sure, and the connections of the various elements of the state bureaucracy that deals with biogas or farms or whatever can really facilitate this and takes out the burden from the livestock farmer or somebody that has limited knowledge of this kind of process. Now, on top of this, I would add, and we have seen this working in other parts on the digitalization program that is taking place in the last 5-6 years in Greece. Only recently, an AI agent was introduced to a number of bureaucratic processes, and I think similar tools can be easily applied to guide people to perform, not just for biogas, but I think certainly digitalization, interconnection of databases, and the use of the new tools that we have been seeing in the last years.
Thank you, Ioannis, for your answer.
Thank you, Ioannis. Okay. I don't think there are any other questions in the chat. No? Okay. So I think we can move on towards the end of the event. First of all, I want to thank all the speaker and the colleagues from IIR and ICP for joining the webinar. I hope that all the audience also that joined this event found the information and the presentation useful. And of course, if you want to stay updated on with the project, with better activities, follow us on our social media and have a look at the website as well as the YouTube channel, as Beatrice mentioned. And I hope this webinar was interesting, and thank you everyone for joining.